So now the only challenge we are going to get is that group there making noise. No, you don't need to inform them. You don't need to inform them. Uh, uh, it is, you know, when you inform them, it will now cause attention. They will have to come and check on what is happening. So, good afternoon. Is it an afternoon or a morning? It's a good morning. So, this technology here should not actually cause maximum attention. No. It is for my own good. You see TikTokers, right? Making interviews here and there, putting microphones here, talking. So we are applying it in education, right? So we are. No, it's okay. I just need the board. I just need the board. Eh? So please look here. Leave the technology alone. Let's focus where? Here. So last time we were able to move up to as far as today is 13th. So we are continuing with our capacitors, right? Where we stopped at the relative permittivity, isn't it? And we say that relative permittivity is the ratio, relative permittivity which is denoted as epsilon r, is defined as the ratio of, originally or generally, the definition is picked from the capacitances, right? So it's defined as the ratio of the capacitor of a capacitor. It is defined as the capacitance of the ratio of the capacitance of a capacitor when that capacitor is having a medium, right? Divided by the capacitor, or the capacitor whose capacitance is not affected by a medium, right? So the ratio of the capacitance of a capacitor, where that capacitor has a medium between the plates, to the capacitance of a capacitor, where the capacitor has nothing between the plates, is the relative permittivity. So this is the original definition of the relative permittivity. But now we went ahead and looked at the capacitance of a capacitor when the capacitor has the medium between the plates equals epsilon, which is the permittivity of that medium in between the plates, times, is it the area of overlap of the capacitor or the plates of the capacitor, divided by the separation between the plates. You don't mind, your audio is not going to be nani here because you don't have a microphone. So you can talk, you can say anything you probably want to say. Then the capacitance of a capacitor, which the capacitor has no medium between the plates, equals the permittivity of the free space epsilon naught times the area of the same, because in this case we are looking at the same capacitor. The difference is one has a medium between the plates and another one has no medium between the plates. So divided by so we are going to take the same area of overlap, the same separation, the same area of overlap, the same set. So what is going to differ is the capacitances, which are different from the fact that the permittive or the insulators placed between the plates are different, right? So now if we substitute these two in here, we shall have relative ER, the relative permittivity or the dielectric constant, equals E A over D, the whole of this divided by E naught A over what? Over D. Now from here, the remaining piece of work is algebraic gymnastics, you see? So if we substitute these two here, mathematically, this separation will cancel with that, right? then the area will cancel with that, such that you remain with the relative permittivity ER equals E, which is the permittivity of the medium placed between the plates, over the medium of air. I mean the permittivity of air, or the permittivity of free space. Free space. So this is also another definition of relative permittivity. So what was the next thing on the agenda? You write measurement of capacitance. Measurement of capacitance. Measurement of capacitance. Measurement of capacitance. So there are two approaches. One, using a reed switch. Measurement of capacitance. Of course, capacitance is of a capacitor. Human city. You simply need, now that you know, you sit on it carefully. Or you can now tilt it like this and use that as the chair. The raw reduction echelon. Of course, we know with time, if there is consistency here and there, even the neighbors, when cars had just come in the world, initially there was animal transport. So later on, technology was advancing, and people came up with vehicles. But the first cars were having ballistic engines, giving too much noise. Combustion could, formation of gases in space. So these people did not embrace the evolution of the vehicles in the first place, because they were like, now, whoa, the noise and what. But currently, a car can even pass just adjacent to this hole, and nobody can tell. So the arrival is disturbing not only you, but even the neighbors. Arrivalism in Luganda is called Amaro. Amaro is disturbing you, but even us, on the first sight of such things, you may not have, but the majority have. And now you are with the majority, so you have to suffer from the. If one frog urinates into water, then we can say frogs have done what? Yeah, we actually generalize and say all the frogs have made it. So how can we determine the capacitance of a capacitor using approach number one, a reed switch? It's called actually a vibrating reed switch, because at a certain point it will be vibrating depending on what we want. If we want to be charged, the vibrations will be completing the circuit with respect to charging the capacitor. Then if we want to discharge it, definitely the vibrations will be completing the circuit with respect to discharging the capacitor. So you can write and say, the switch is closed. The switch is closed after connecting the circuit as shown above. The switch is closed after connecting the circuit as shown above. The switch is closed after connecting the circuit as shown above. The switch is closed after connecting the circuit as shown above. Full stop. The microammeter reading I. The microammeter reading I the microammeter reading I the microammeter reading I is taken together with the voltmeter reading V. The microammeter reading I is taken together with the microammeter reading I is taken together with the voltmeter reading V. Full stop. Knowing the frequency F of the AC in the reed switch, knowing the frequency F of the AC, what is AC in full? Yeah. What is AC in full? What is AC in full? Alternating current. So alternating current is provided or is showed on the circuit here. So if we know the frequency with which the AC is being supplied, So knowing the frequency F of the alternating current in the reed switch circuit, knowing the frequency F of the AC in the reed switch circuit, the capacitance of the capacitor is calculated from 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 C equals I out of FV. C equals I out of F what? FV. So once you connect your circuit as shown on the board, you complete, then the vibrations begin due to the alternating current. You know, alternating current is that the current that flows to and fro. That's why it's called alternating. It keeps changing the direction. So it's the one that gives us both charging and discharging of a capacitor. Alternative B, using a ballistic galvanometer. Using a ballistic galvanometer. Another method of charging a capacitor, determining measurement of capacitance of a capacitor. Using a ballistic galvanometer. Using a ballistic galvanometer. But you guys, we had agreed that you fix this board, didn't we? Using a ballistic galvanometer. So in all circuit experiments that you can be actually tasked to carry out, you guys are not doing anything as per writing is concerned. So I'm saying that for all circuit experiments where you can be tasked to either measure, determine, after organizing or arranging the circuit the way you think is right, then you take us through the steps of what to do to achieve what, and what. Then finally, in your conclusion or in your as you are concluding, you must show either if that parameter that you are trying to measure is calculated, you show the expression by which that parameter can be calculated, or if it can be read directly from any of the components that you used in the circuit, you still also inform that the current can be also determined in that way, or that parameter or that quantity you're trying to measure, still you mention that it can be read from either, if it is current, from an ammeter, if it is PD, from maybe a voltmeter, and any other quantity to mention but a few. So now in this case, we are looking at capacitance. That's why our final expression has the capacitance equals to the current, which current was directly read from the circuit. And in the circuit, we have an diameter that can try to help us to measure the smallest current. Then we have a voltmeter that is going to measure the PD that is across the capacitor. And then we have the frequency of the AC source that can be a known value. So for the ballistic galvanometer, the capacitance of the capacitor C1 I beg my pardon. The circuit is connected as shown above. 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 Of course, now to avoid the other too much wording that you can say, connect a source of EMF. This is a source of EMF, maybe PDV. So after the diagram is drawn, then you can refer to the diagram. So the circuit is connected as shown above, a full stop, bullet 2. First with a standard capacitor. First with a standard capacitor. First with a standard capacitor, CS. First with a standard capacitor, CS. First with a standard capacitor with denoted as CS, C subscript S. First with a standard capacitor, CS, C subscript S. We are meaning that in the circuit, before we connect this capacitor, whose capacitance is to be determined, we shall put in a capacitor whose capacitance is known. Then we determine the deflection of the ballistic galvanometer. We denote the deflection. Then we bring in a capacitor whose capacitance is to be determined. Then we also note the deflection. Then we juggle what we shall have achieved mathematically and get the capacitance of the capacitor. So we say that beginning with a standard one here, you complete, you charge it, then you discharge it through. When you fix in a standard one here, you begin by charging it, closing a switch K1. Thereafter, you discharge it, open K1 and you close K2. Then you determine the deflection of the big E, which I'm calling the ballistic galvanometer. Then after you have the deflection of the big E and the capacitance of the capacitor, which is a standard one, CS, then you remove it, put in the one that you want to determine the capacitance. Then you do the same thing. Are we together? After, because you are, you can go take some water and come back. So then after you've put in this one, you do the same thing and then you compare the ratios as we are going to see in our mathematical calculations of how to compare the ratios of CS and the deflection must equal to the C and the deflection. Are we together? So we say first with a standard capacitor of capacitance CS, comma, switch K1 is closed. Switch K1 is closed. Switch K1 is closed. Switch K1 is closed. And after a short time, it is opened, and after a short time it is opened, and after a short time it is opened. Full stop. Another step. Switch K2 is now closed. 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 And the deflection of big E and the deflection of big E theta subscript S is noted. And the deflection of the big E I've said it's ballistic galvanometer, and the deflection of the big E is noted. Full stop. Another bullet. The capacitor is replaced with the test capacitor. We are replacing a standard capacitor with a test capacitor. The capacitor is replaced with a test capacitor. The capacitor is replaced with a test capacitor of capacitance C, and the capacitor is replaced with a test capacitor of capacitance C, and the procedure repeated. And the procedure repeated. And the procedure repeated. Full stop. The deflection theta of the big E is noted. The deflection theta of the big E is the deflection theta of the big E is noted. Is noted. The deflection theta of big E is noted. Full stop. The capacitance of a capacitor is calculated from the capacitance C of the capacitor is calculated from the capacitor of a capacitor C is calculated from the expression C, which is the capacitance of the test capacitor, equals the ratio of the deflections, the one of the test capacitor to the one of a standard capacitor, then times the capacitance of a standard capacitor. Of course, we know that for any ballistic galvanometer, the deflection depends on the capacitance, and it varies as a proportional. So we shall have CS proportional to theta S, and then C proportional to theta. If you divide these two equations, then they are constants of proportionality that shall have emanated from the fact that we have these two signs. So if you divide this by this, you will have an expression which is CS equals theta S over theta C. If you make this the subject of the formula, definitely you will drive back to that. Are we together? But the best way is to check on here, what did they divide by what? So in this case, we divided the capacitance of a test capacitor varying proportionally with the deflection of the ballistic galvanometer divided by CS divided by theta S. So at the end of the day, you get C, the capacitance of the capacitor, equals theta over theta S times the standard capacitor. Capacitor network, subheading. Capacitor networks. Capacitor networks. capacitor networks. So capacitors can be arranged Younger, I will pick you from behind there and put you in front somewhere. Or else you will make me develop the morale and buy another camera, such that I focus one on my board to get my information, then another one in the audience for to monitor the audience. Now let me tell you, I personally, I did not start this. Let me even stand in front of the camera, such that that man can observe that what he taught us is being put in practice. The man who taught me physics at Makerere was called Mr. Benon Fred Twinamasiko, who used not to make noise with the students. All his lectures are posted on YouTube. So if you want to understand more about his physics, you can check on his page on YouTube, and definitely you can actually understand more. The reason we are doing this is simply to make sure that, at a certain point, you can get access to the internet and you're like, let me check on Israel's teaching. You go on YouTube, put in Tevandeke Israel Kayondo, then you get, and then you choose which one you want. But this man, number one, he used to supervise his exams alone. Imagine at the university. How could he do it? He had 2 camcorders and 2 stands like these ones here. So he places one here, then he places another one there. Focuses on the learners or the audience. He goes to his office and chillax. You copy his exam, you do the same. Students and Ugandans especially, we think this man puts these things for formality. Well, once he watches any clip into the video that, my daughter, what is your name? Dina. Once anything crops up and Dina was trying to look through a neighbor's work, the man picks out that clip, brings it in class for evidence, such that your marks do not come back when you know that I cheated. And the guy did not do what? Release my mark. So after you have been caught cheating an exam, a video is displayed on the smart board when Dina is looking into the neighbor's work. And then he tells you that you have no marks. So in his course, there was no cheating. It was a must attend. So in future, when I get some good money, I will also get 2. One to record whatever I'm teaching on board here, another one to focus. When my daughter the other side tries to look at the neighbor and smiles, that is a retake. That's what? A retake. So capacitors can be arranged to form a network. Are we together? Capacitors can be arranged more than 1 or 2 to make a network. Now the arrangement of the capacitors determines the effective capacitance that you will get. The arrangement of the capacitors determines the effective nani that you will get. The arrangement is clustered into 2. The arrangement is grouped into, one is called parallel what? Arrangement. And the second one is called series or series arrangement. Parallel arrangement and then series array, depending on what you want. If you need too much or a bigger capacitance compared to the one that you have from individual capacitors, you need to determine what kind of arrangement are you going to use to achieve that. However, what if you need a smaller one? but you have a number of the capacitors that you need to put in the same circuit. Again, what type of arrangement are you going to use? Now let's try to analyze one by one. Let's begin with a series arrangement. Let's begin with a series arrangement. So in this case, they are arranged one to the other. I mean, from one, the connection continues to the other. This is what we mean. One plate is connected to another plate in the sense that when charge flows from the source, it can be distributed throughout the plates equally. Are we together? The charge that goes on each plate of this arrangement of the capacitors is the same. Is the same. So if you have a source of charge with a potential or a PDV, and then this is a capacitor with capacitance C1. Let us assume these three are not the same capacitance. Then this one is a capacitor with capacitance C2. And then this is a capacitor with capacitance C3. Are we together? So in this case, if you arrange them in series, you will have the same charge on each capacitor. So this will be having the same charge too. This one will also be having the same charge too. And then this one will be having the same charge. Now we are considering a case of only 3. But they can even be more than 3. Are we together? So having the same charge on each, it means that then the PD across each is not going to be the same, right? The PD across each is not going to be the same. So in this case, we are going to conserve the charge. The charge that was produced, I mean the PD, we are going to conserve the PD, I'm sorry. We are going to conserve the what? The PD. So in this case, the PD that the source gives out, in this case, the PD that the source gives out is going to be shared by each basing on how strong the capacitor is. Because we remember that from capacitance being, how did we define the capacitance of a capacitor? I'm sorry, but this one in front here. Hey. How did we define capacitance of a capacitor? This man here, generally, not the one of parallel plates. You are slumbering. Anybody can try to remind us? How did we, from first principles, define capacitance of a capacitor? The ratio of the magnitude of charge on either plates of the capacitor to the PD between the plates. Are we together? Which means that now each capacitor will take a different portion of PD basing on its capacitance. And that one will happen in a way that they will be inversely proportional. The one with a big capacitance will take a small PD. Isn't it? The one with a small capacitance will take a big PD because capacitance is inversely proportional to the voltage or the PD. Are we together? Tell this Mushirambu too. Mujama. So now, conserving the PD or the energy, we shall have that the V that we supply or we connect, having the V that we connect across all the three, it will not be wasted, right? It will be shared by each kappa. So the capacitor of C1 will take V1, right? A capacitor of C2 will take V2, and the capacitor of C3 will take V3. And therefore, substituting for by each PD, because if C equals Q over V, if C equals Q over V, those mathematical giants, what will be V if you make V the subject of the formula here? What will it be? It will be V equals Q over C. So we shall have, this is the total PD that was supplied by the cell. Then each capacitor is going to have its own PD, which is V1 equals Q over C1. Because we say that the charge is the same on each capacitor. So V2 is going to be Q over, and then V3 is going to be Q over C3. So we shall substitute here and have V equals Q over C. So Q over C equals V1 is Q over C1 plus V2 is Q2 over Q over C2 plus V3 is Q over C3. So I want you to convince yourselves mathematically that this charge will cancel throughout, right? So we shall have 1 over C equals 1 over C1 plus 1 over C2 plus 1 over C3. So now the effective capacitance that you will get after arranging your capacitors in series arrangement is going to be the reciprocal of that effective capacitance will be the reciprocal of the capacitance of C1 plus the reciprocal of the capacitance of C2 plus the reciprocal of the capacitance of C3 and plus other many. If you have more than them, they will be plus other many, then plus 1 out of Cn, where n is that maximum number of the capacitors you have. So now, if we now try to check what will be the capacitance if we only have 2. If we only have what? Have 2. Students can convince themselves. 1 out of C equaling to 1 out of C1 plus 1 out of C2. Question, what will be C from this case? What will C be in this case? C is going to be C1, C2 over C1 plus C2. Check mathematically if it's what you get. Check mathematically if it's what you get. Check aside and see if it's what you. First, do what I have said. Check for the mathematics. Is it coming out? Eh? Human. Is it? I've said check. Yeah. Human communicating through the window. They are bad manners. So now let us assume C1. Let us assume C1 is say 1 Faraday. Let us assume C1 is 1 Faraday and C2 is also 1 Faraday. What will be C? If C1 is 1 Faraday, you can check as well and tell me what will be the value of C if C1 is 1 Faraday. Do what I'm saying. You will take notes later. If C1 is 1 Faraday and C2 is 1 Faraday, that is what we are using. That's why I've said check. Huh? Which answer? So you guys, this is wrong. Huh? It's wrong. C is not equaling to C1, C2 over C1 plus C2. Come. Come. You are going to explain, right? Put it. No, you can hold it.
Here. Here, what I was saying, you are saying here.
Can we listen?
For here, this is like the LCM.
A Europe of the top part.
It was C is equal to C1 plus C2. This was over. I made a mistake. This is 1 over C1 plus 1 over C2. Now if you want to make the equation, you have to first look for the LCM. C is equal to.
Should we give him more time to take us, or he stops there? Because he's already wrong. Give the microphone to someone who thinks can give us. I mean, that person, you come and take us through. You people, that's the I bought it money. So you put it on top of the desk.
It is 1 out of C, which is equal to 1 out of C1 plus 1 out of C2. LCM, it is C1 and C2, which is 1 out of C is equal to the LCM C1, C2. Then it is 1 out of C1 times the LCM, it is C1 times C2. Brackets, then plus 1 out of C2 times C1 times C2. Then this C1 will go with this one will move with this one. We shall remain with 1 out of C, which is equal to 1 times C2 plus 1 times C1 out of C1, C2. It is 1 out of C is equal to C2 plus C1 out of C1, C2. Here we cross multiply. We shall remain with C equals to C2 plus C1 out of this one and this one will remain with C1, C2. This is the answer.
This person had actually made it better, but she went off by 1 step. Is there any mathematician who can correct that? Give the microphone to her. Don't rub off her work, just rub off this one on the other side. Rub off this one. You see how your mathematics is in ICU? Okay, let's give her a chance.
This is 1 out of C equaling 2.
You start from that step where she has gone wrong.
Wait.
1 out of C equals C2 plus C1 over C1 C2.
Hey, how are you?
No, the step just the second last, yes, there.
That's C2 plus C1 out of C1 C2. Then here when you cross multiply, you shall have C1 C2 equaling to C into C2 plus C1.
Are you putting on the microphone?
Yes.
Make sure that I get the audio
Then
on
here,
editing.
we shall divide both sides by C1 plus C1. C2 plus C1. Here C2 plus C1. This goes with this one. Then we remain with C equaling to C1, C2 out of C2 plus C1.
Let us give her a round of applause. So you see how your the nani maths is limping. Eh? It's limping. You know to limp. Your mathematics is limping. But good try. This person had actually made it. But now here, this is, remember, if this is already a reciprocal, okay, and it is equivalent to this, where the numerator is sum and the denominator is product. Honestly, can it be the same even when you take C into the numerator of the reciprocal? It can't be the same. So in mathematics of the primary, where like once you bring out this from the reciprocal form, now you switch the other parts of the fraction. There was a numerator, it becomes a denominator, and there was a denominator becomes a numerator. So that is one form. So I was telling you to check what will be the value of C if C1 is 1F and C2 is 1F. You realize that C1 is 1F and C2 is 1F, right? What will be C? Check again mathematically and see. We want to conclude by asking if we need a smaller capacitance, what arrangement do we consider? And when we need a bigger capacitance, what arrangement do we consider? Please check. Feed in the values in that expression, C1 and C2. Human do the same. Pardon? It's what you get. What do you get as C? C is a half, 0.5. Right? Which means that if I have a number of capacitors, all right? If I have a number or numerous capacitors, my daughter here, are we together? If you have a numerous capacitors and you need a smaller capacitance of the combination, what is the best or what is the suitable arrangement? Huh? You answer me. If you need a smaller capacitance from a number of capacitors, what is the suitable arrangement? Series. Because you realize that for C1 is 1F and C2 is 1F. But what you get after the combination is less than the individual capacitances or the capacitors. Are we together? So which means that if I have a number of them and I want to use all of them, but I want to get an effective capacitance which is smaller than any of them, I arrange them in a series manner or arrangement. Now let us look at the parallel arrangement. Parallel arrangement. For parallel, capacitors are arranged in a manner that they share the same PD. For parallel, capacitors are arranged in the sense that they share the same P. The PD across all the three, or all the, according to the number that you'll have, is the same. But now, because of the junction at a point, the charge that is going to be taken by each is going to be different. So the PD that you apply is going to be the PD across all the plates. So if this is C1, C2, C3, we are saying that the PD across all the plates is the same. So in this case, the quantity that is going to be different on each is the charge. So this one will have a different charge, Q1, right? This one will have a different charge, Q2, and then this will have a different charge, Q what? Q3. So in this case, what are we going to conserve? The one that has been shared or distributed is the one that is going to be conserved. That what you supplied was not wasted, but everybody picked according to their capacitance. So now in this case, from the fact that C equals Q over V, if we hold V as a constant, it excuse me, it will mean that C is directly proportional to Q. So which means that the one with a bigger capacitance will absorb a bigger charge. So in this case, conserving charge, the charge that you distributed or that you supplied from the cell equals the charge that a capacitor with capacitance C1 it grabbed, plus the one that was by the capacitor of capacitance C2, plus the one of the capacitor whose capacitance is C3, Q3. Yes. I'm saying that is if Q1 has the higher capacitance. Yeah, because capacitance is directly proportional to charge. From here. Why? This man is reasoning as somebody who thinks that people who sit in front of the bus arrive faster than those who have sat behind the bus. Eh? Literally, it's what he's trying to mean. That this one that is close to the source will absorb more charge. Not so. I mean, it's not the case. It's not that tall people receive rainfall faster than short people. No, we all get that rain at the same what? At the same time. So now, substituting for Q, if C equals, ladies and gentlemen, you come back. If C equals Q over V, what will be Q? Q will be CV. So which means that Q1 will be C1V, Q2 will be C2V, and Q3 will be C3V. So we shall have, this is CV equals C1V plus C2V plus C3 what? V. So again, convince yourselves mathematically that this V can cancel throughout, right? So we shall remain with the effective capacitance as C equals C1 plus C2 plus C what? So if you have more than 3 capacitors, let us assume you have n capacitors, it will be plus other many plus C what? Plus Cn. Now here there is no algebra that we can check whether it is correct. It is direct, right? Now again we need to check if C1, let us assume we have 2 capacitors which equal to whose capacitance is C1 plus C2. What if I have C1 as 1F and C2 as 1F? What will be C? It will be 2 what? Which means that if I want a bigger capacitance from the numerous capacitors that I have, the possible arrangement to give me that is parallel. Can you take your notes? Take notes according to what you've understood. Take notes according to what you've understood. Hurry up. Take notes, analyzing the two forms of. You guys either come to physics or you go to where? Madam, what do you want through my window? Are you sure you don't want anything? Examples 1. Human, take note. Write what you've understood. If you haven't understood, again you tell us and we know. There is a hand out there. I can see you sweating plasma. Human, bring that hand out here. Hey. Bring, don't worry. Open where the networks are. Take the notes very fast. I think the taking notes is done, right? Let's look at a few numerical examples. Let's look at a few numerical examples. Have you solved the example? Huh? Would you try one? Huh? Or you fear the camera will switch it off? Let us try example one as a class. You can write and say a battery of 12 volts, a battery of EMF 12 volts, a battery of EMF 12 volts, a battery of EMF 12 volts is connected across. A battery of EMF 12 volts is connected. A battery of EMF 12 volts is connected across a system of capacitors. A battery of EMF 12 volts is connected across a system of capacitors. Full stop. Calculate the effective capacitance. Calculate the effective capacitance of the system. Calculate the effective capacitance of the system. Calculate the effective capacitance of the system and hence find the charge on Roman 1. Hence find the charge on Roman 1 each capacitor. Find the charge on each capacitor. And then 2, the total charge of the system. Yeah, man, what is this? What is this? This is where your witchcraft is. Okay, don't leak it anymore. Put it in the pocket. The total charge of the system. Find the total charge of the system. I wanted to give chance to another person again in front here, such that I do not over appear. Or I try this, then the audience will try the next. All right, so first we are looking for the effective capacitance. Now you begin by asking yourself, tapping onto each capacitor and another one, asking yourself what form or what type of the arrangement the two are. So as a matter of fact, can we start with this and this? No, so we look at those ones that are actually in the same vicinity and the type of arrangement that is associated with them. So initially you look at this and this and then ask yourself what is the form of arrangement is that? Parallel. So what is the effective capacitance for capacitors in parallel? It's, should we go 1 out of C equals 1 out of C1 plus 1 out of C2? So what is the effective capacitance of capacitors in parallel? C1, we are talking about parallel. So it will be C1 plus C2, because these two are in parallel, right? So we shall have the effective of these two here as what? Let's call it CP. It will be 2 plus 3, which gives us our CP as 5 microfarad. So if we can try to redraw the circuit here, we shall have something like this. Where this one is 5 microfarad, this one is 5 microfarad, and this was 12 watt. So what will be the effective capacitance of two capacitors in series? Pardon? It is C1, C2 over C1 plus C2. So we shall have our C as C1 5 times C2 5 over C1 5 plus 5. So we shall have our C as 25 over, which is 2.5 watt microfarad. That is the effective capacitance of the system. That is the effective capacitance of the system. I said stop leaking this thing. Human, why didn't you contest for prefecthood? You are not a politician. Yeah? Currently, politics is serious business. You don't want money. first put units. When I rub off this, what else are we finding? So our effective is 2.5 microfarad. What are we looking for now? Eh? The what? The charge. We are beginning with charge on each capacitor, right? Yes. So we are beginning with the charge on each kappa. So if we call this capacitor C1, we call this C2, then this C what? C3. The charge on these two, the charge on these two is not going to be the same because they are in parallel, right? Are we together? The charge on these two is not the same. So we shall have charge Q3 and charge Q2, right? Are we together? But now the charge on the combination of these two is the same as the charge on this. Are we together? The charge on this, which is the effective, the combination of these two, is the same as the charge on this because they are in series. Are we together? So we start the game. Then if the charge here is not the same, so what is the same there? What quantity do these two capacitors share as the same? Yeah? The P, the PD. So the V here, if we can call this V2, yeah? Then this is going to be V what? V1. Huh? Are we together? Are we together, please? The V that is across two capacitors in parallel is the same. It's only the charge on their plates which is not the same. But now for series, the V is not the same. It is the charge which is the same. So I actually used to say that for parallel, the fact that it starts with a P, the PD is the what? Is the same. Are we together? Then for series, because now in pronunciation you hear it is series, but you know, because the majority here, you did not go to well-grounded kindergarten, so you pronounce these words as they are. So for me, in my accent, I will say this is series what? Arrangement. So because of the C, it is the charge that is what? Is the same. Are we together? So for parallel arrangement, PD across all those resistors that are arranged parallel is the same. Then for series arrangement, all those capacitors arranged in series, their charge is the same. Are we together? So then we come here and look at now, if these ones are in parallel, the PD across this is the same as the PD across that. But they are in series, so the PD across this, we can call it V1, okay? And the PD across this is V2. So we can begin by getting the PDs, V1 and V2, right? V1 is going to be Q over C1. Yeah. V1 is going to be Q over C1. So V1 is, we do not know, but Q is what we are looking for. Oh, V1, do we know? We don't know. Even Q. $12 is the total that we can get from V equals V1 plus V2. So we need some charge there. We can begin by getting the total charge of the system, right? Huh? Can we start by getting the total charge of the system, which will be Q equals C over V? Okay? So Q is the total charge of the system, which is what we are looking for. Then C is the capacitance of the system, all right? Which we have as 2.5 times 10 to power negative 6. All over. Are you sure that is the formula? Is that the formula for finding Q? I think Q equals C from C equaling to Q over V. Q will be CV. So from Q equals CV, Q is going to be 2.5 times 10 power negative 6 times V, which is 12. What do you get as Q? Pardon? 3 exponent negative 5 what? Coulombs. So this one can be written as 0.3 micro coulombs. Is it 0.3 or 30? So in this example, it becomes hard for us to find the charge on each capacitor, because at least we need to know a particular charge of 1, then we use it by breaking from one charge to, from one capacitor to another. Am I clear? We may find it difficult to find the charge on each unless we have at least one charge of the other. Then we can use it to find the one of the other one, then we reverse what is it. Eh? Are we together? Are we together? We cannot find the charge of each. This unless at least we know the charge on either of the three. Am I clear? We at least need to know either the charge on this, then we use it to get its PD. Then after getting that PD, we get the PD across this. Then using that PD and the capacitances, we can get the charge on either. So that one is nullified. Can I rub off this one particularly? So you can write and say the diagram above, the diagram above, the diagram above shows a network of capacitors. The diagram above shows the network of capacitors connected to a 120 volts supply. Connected to a 120 volts supply. Connected to a 120 volts supply. Calculate the Roman 1. Calculate the Roman 1. Calculate the Roman 1. But only that we don't have time. Who is that one? Tell him to go through. Only that we don't have time, but I think we can create two simultaneous equations there and get. Have you started solving simultaneous? I think we can create two simultaneous equations here and have V1 plus V2 equals what? Equals 12, right? Huh? Let's cooperate. V1 plus V2 gives us a 12. But the charge on this is the same as the charge on this. Okay? So we shall have, this is Q. What is V in terms of Q and C? Q over C, right? So Q over C plus, if we denote them as 1, 1, Q2 over C2 will be 12, right? Yeah? So this Q is the same, right? This Q must be the same because they are in series, right? So we shall have Q into 1 over C1 plus 1 over C2 equals 12, right? Huh? Are we together? Are we together? Who is saying no? Are we together, please? Yes. Eh? So this Q is what we are looking for. Into 1 over C1 is 5 plus 1 over 5. But these ones are supposed to be converted from micro to the Faraday, right? Equals 12. So that Q is going to be, yeah, add this and see what you get. You will get 2 over 5 equals 12, such that we get Q into 2 over 5 exponent negative 6 equals 12. Is it mathematically the same? Yeah? Is it the same? 1 out of 5 exponent negative 6 plus 1 over 5 exponent negative 6, what do you get? Yeah, we get this. So by 2 ones by 2 6, multiply 6 by 5 exponent negative 6, what do we get? You get 3 exponent what? You get 3 exponent negative 5. So can we apply this? The charge on this is this, right? The charge on this capacitor is this, right? So we can have from Q equals, is it CV? CV, so the charge is 3.0 exponent negative 5 equals the capacitor, which is 2 exponent negative 6 times V1 that we are looking for. So divide 3 exponent negative 5 divided by 2 exponent negative 6. Eh? What? Should we take 5? We take, oh, this was 5. Now, which means this answer is wrong. It must be wrong. Auntie, even this is supposed to be 2. Which one? It was what? It was 5. Sorry. So if you take 5 here, even where? Where? Here. This 2, it came from the fact that 1 out of 5 plus 1 out of 5. What do you get here? 3 exponent negative 5 divide 5 exponent negative 6. You get 6. So V1 is 6 volts. Right? Huh? Which means even V2 is going to be 6 volts. You agree? Huh? Such that, from where? From here. Huh? I said after getting Q, the charge on each capacitor, which we calculated as 3.0 exponent 5 coulombs. Now we are going back to each capacitor to get the PD. If this charge is on this and the same charge is on this because they are in series, then we can now split the equations from C this equals the charge on this over V, which V is V1. That's what I'm doing here. Actually here. Such that I get my V1 as 6. Now if V1 is 6, from V1 plus V2 equals 12, even V2 will be 6. Right? Such that 6 plus 6 gives you get a 12. Now you can use even those facts and get the charge on the other diagram that we had. Are we together? So you just needed time. Anybody can try this and we go for lunch? Yeah? You want to try? Feel free. The question was calculate. The question was, the diagram above shows a network of capacitors connected to a 120 volts supply. Calculate the charge on the 4 microfarad capacitor. Calculate the charge on the 4 microfarad capacitor. Studying through the window is not acceptable here. Calculate the charge on the 4 microfarad capacitor. I give you my microphone. No, I need to capture the audio. You come and I fix it on your collar.
And from here we have the capacitors arranged in parallel. Then here we have to have it in series. Here we shall get 4 plus this one. Then we make 5. Then here we redraw, have then this is 5 microfarad. Then here we have 2 microfarad. And then here we have the voltage 120 V. Like this. Then this is the series arrangement. Then from there we shall have C equaling to C1, C2, C3, then out of C1 plus C2 plus C3. And here
Will it be the same thing, you people? Mathematically? I think for that case, let us use the 1 out of C equals 1 out of C1 plus 1 out of C2 plus 1 out of C3.
One out of C going to 1 out of C1 plus 1 out of C2 plus 1 out of C3. And here 1 out of C equal to 1 out of 2 plus 1 out of 5 plus 1 out of 2. Here 1 out of C equals 2. Then we find the LCM of these ones. That is 10. And we get 10 divided by 2. 5 times 1 is 10 plus, that is 2. 10 plus 5. So I get 1 out of C equaling 2. This is 12 out of 10. By cross multiplication, we shall have C have 10 equaling to 12C. The remain with C equaling to 10 out of 12. Then what is C? 0.83. That is 83 micro. What was the question? What? Of 4.
the charge on the 4 microfarad capacitor?
This one.
Mm.
Ah. Here we have C1 equaling to Q out of V1. See that is in parallel arrangement, and in parallel arrangement we see that the PD of all capacitors, it is the same. So here I have 4 equaling to Q out of 120. I have Q equaling to 4 times 120. Here Q will be equaling to 480 microcoulomb.
Oh, God, that charge is too much. Should we go by her suggestion, opinion? Anybody can give a correction? Is there anybody to help us there? Please, those guys who are sleeping, are you part of us or us is part of you? So one thing our sister has to do first is to get the PD across these ones here. The PD across this, call it V1. Yeah. Can we look here, everybody? If she gets the PD across this and all of these ones are in what form of arrangement?
Parallel.
This one and this and this are in what? So the PD across this as V1, the PD across this as V2, and the PD across this as V what? V3. Yeah. So when she adds this V plus this V plus this V, she will get 120, right? Are we together? Are we together, my daughter here?
Yes.
If you add the PD here plus the PD here plus the PD here, you get one what?
120.
But for this form of the arrangement, the charge here is the same as the charge there, is the same as the charge there. Because they are in what? Series. Are we together? Now, once you get that PD, you are going to substitute for that PD with Q over C. Is it? PDV equals Q over, from C equals Q over V, V will be Q over C. So you substitute for Q over C1 for this case, right? Are we together? Plus Q over C2 for this case, plus Q over C3 for this what? Case. So the Q is the same, you factor it out. Are we together? Then you substitute for the C1, C2, and C what? C3. Right? Are we together? Then you get this Q, which is on these 3. When you get that Q, it's the one you will use to get this V1. Are you getting the point? From Q equals CV. Use this Q and the C you know to get this V1. Use the same thing. You have this V. You have this C. You have the Q. Then you get V2. Are we together? Then use this C and this Q. You get V3. Are we together? Now the V2 is the one you will use here. You understand? To get Q of the combination here. Are we together? When you get this V, you use it to get this Q. When you get that V, when you get that V, when you have this V, V2, you use it to get this Q. This, what are we getting there?
We want charge.
When you get that V, remember these two are in parallel, right? So they have a V which you got as V2, right? Now, you need the charge because the V is the same. You have the capacitances, you can find the charge on the 4 microfarad copper. Are we together? Are we together, guys, here? The problem is you are looking at people outside there. You man, are we together here? Can you try this number? Now why are you saying yes? Me, I don't care. I will make you stay here. Now, you are going to do this in my presence. She redrew this and she has this as 2 micro, right? Everybody hold a pen and a calculator and a piece of paper. Then she has this, which is this and this, to a 5 watt, right? Then she has this as what? 2 micro. Then she has the source. This is 120. I want to see everybody writing, including you. We are looking for the charge on the 4 micro copper capacitor. I am saying that if we can get, because these 3 are in what form of arrangement? So their PD is the same? Are you sure?
No, the charge.
So the PD here, if we can call this C1, it will be V1, right? The PD here, it will be V2, right? And the PD here, it is going to be V what? V3. Now we are starting by conserving PD, which is V1 plus V2 plus V3 equaling to 120, right? I've said I want to see everybody writing. V1 plus V2 plus V3 is 120. That is one fact. But what is V in terms of Q and C? V will be Q over C. Substitute for each here, holding the charge the same. Can you guys go to your class? Holding the charge the same, substitute for V. V1 as being Q over C1. Now factorize Q. Put it outside. Now substitute for C1 because you know C1, C2 and C3. Substitute them as micros. Ask me, I am here. Even him is confused. When you're pressing your computer, make sure that you cater for the micros. 1 out of 2 micro. Younger, I've not talked about this. I want to see everybody doing what we are talking about. I'm not getting you. I'm not seeing what you're doing. How far? I will take you in front there. I've talked about step by step. You man, go to your class. What? Micro is negative 6, exponent negative 6. My brother, you were too slow. I've said V1 plus V2 plus V3 is 120. Substitute for V in terms of Q and C, where Q is a constant. So factor it out. Write and say Q over C1 plus Q over C2 plus Q over C3. Isn't it? Equals 120. But Q, because they are in series, is the same. You factor it out. Q into 1 over C1 plus 1 over C2 plus 1 over C3 equals 1 what? Do you know this? C1, A. You know C2, you know C3. Substitute. Putting in consideration their micros, also put them there. You are lying. The micro should be part. When you are calculating anything, make sure that the micro is considered. Put it in your substitutions. What are you looking for? Yeah? I said this is V1 plus V2 plus V3 equals the total PB that was supplied. Then, what is V in terms of Q? It is this. But because of the fact that the capacitors are in series, the charge is the same. So we shall have V1 equals Q over C1, V2 equals Q over C2, V3 equals Q over C3.
What?
Isn't it? Are you getting me? Then you substitute this here. When you substitute them here, you'll have Q into 1 over C1 plus 1 over C2 plus 1 over C3 equals 120. You know C1, you know C2, you know C3. With their micros, using a calculator, you press this and get the answer. You get the value of Q.
Negative.
Ladies and gentlemen, how far? What do you have as Q? 1 point? The Q you have is 1. Is it what you have? Switch off the microphone. It's what you have. You people, they have a different answer here. What do you have there? 1.0 exponent negative 4. Your dinner? What do you have? You will not go for lunch if you don't finish this number. You have what? You have 1.0. So your Q is 1.0 exponent negative 4 coulombs. But it is not the charge on the 4 micro. It is not the charge on the 4 micro. It is simply the charge on this, on the combination here and on this. The charge on this, this and that, and that. Now what do? We come now back here. We come now back where? If you know this as your V2. If you know this as your V2. Are we together? Are we together, guys? If now we have our, because our V1 is going to be that charge. Where did I write? Our V1 is going to be that charge over C1, right? This V1 that we don't know is going to be that charge, which is 1.0 exponent negative 4, divided by what? C1, which C1 is this, right? Then V2 is going to be Q over C2. It's going to be this charge over C2, which is this, right? Then V3 is going to be Q over C what? Is going to be Q over C3, which is this, right? Are we together? Now, once you have your V2, which is across this, huh? If you have your V2, which is across, it is going to be now C equals Q over V. You have V2, which is this. You have C, which is this. And then you have the charge, and you're looking for the charge. Are we together? Are we together? You have your V2, which is this. You have C, the 4 microfarad capacitor. You want the charge on the 4 microfarad. Can't we get it now? Therefore, I beg to stop there.